Hey you guys, it is me, Dr. Myers, here, hoping that you were able to get this lecture set up. If you're watching this, that means we hopefully were successful, and hoping you'll be able to see the board okay here. The plan for today, as you know, you've got homework due. I do have your first homework one graded, and my lovely wife will distribute those papers to you guys. You're welcome to look at any comments that I have. Like I said when I talked to you guys about homework before, I didn't grade all the problems. I just picked a few and graded those. Please look at my comments. You guys are welcome to correct those. You've got about a week to get those corrected. If you've got questions on those, you're welcome to send those to me. What we're going to do today is we're going to go over the second homework that's due today. And I'll just briefly review what's potentially going to be on the quiz. We have a quiz tomorrow. And then we'll go, because today's short, you guys are probably like, yeah, it's short. Because it's short, we'll just have a really short lesson. We are going to talk about logarithms today, because we got to talk about it at some point. And then tomorrow, we'll talk about inverse trig functions. So we've been talking about inverse functions, and we're almost done with all the prep that we need for calculus. So we're going to talk about inverse trig functions and then transformations, so shifting graphs around and flipping them and other stuff like that. So we'll talk about inverse trig functions and transformations, shifting graphs around tomorrow. But today, we'll be talking about logarithms. So let's take an opportunity. We're just going to pray here, and then we'll jump into what we have. Father, thank you again for today. Thank you for the marvels of technology that even when I'm recording this is at a different time than when my students are listening to it. But God, that you're with us in all of these times too. So we lift this time. We pray for understanding, that you would make things clear to us. Help me to be clear in my explanations. Help us all to work hard and to lift everything that we have to you. In Jesus' name, amen. All right, so you have, like I said, we've handed back homework 1. You guys have homework 2 due. And I am assuming that you guys probably have a couple of questions on homework 2. And what I'm going to do here is I'm actually going to try to guess what your homework questions are on homework number 2. Hopefully I catch the problems that you actually have questions on. Remember that homework 2, even though I wrote 5.1 and 5.3, 5.1's out because we didn't have a chance to talk about logs yet. So the questions that are due today are just the 5.3 questions. And the ones that I'm guessing you have questions on are 35 and 45 and potentially 66. Did I guess them? Okay, so let me talk about 35, let me do 45, and then we'll see. We may do a little bit about on 66. I may kind of start you on it. So let's first talk about 35. So on number 35 from section 5.3, we're given a function. In this case, the function is the square root of 4 minus x squared. And they restrict the domain, and you'll see why they restrict the domain in a second. So my function is 4 minus x squared, the square root of that. And what we're supposed to do is we're supposed to find the inverse function and graph f and its inverse function. Okay? So when they say find the inverse function, that means algebraically find the inverse function. And then we're also going to graph the function and look at what the inverse function is. And something really funny happens here, and you'll see why when we look at the graph. But remember, to find the inverse function algebraically, what do? We switch x and y, and we solve for y. So our function here is y equals 4 minus x squared. So what I'm going to do is I'm going to switch x and y. Hopefully you guys can see this. So I get x equals square root of 4 minus y squared, and now I'm just going to solve for y. So to unpeel all of this, first I'm going to square both sides, so that'll get rid of that square root. And then I'm going to add the y squared over here and subtract the x squared over here. So I'm going to kind of do a switcheroo here. So let's add the y squared over. So I get y squared plus x squared equals 4. That should actually look familiar if I just stop for a second. That's actually the formula for a circle, and you're going to see that when we get to the graph, that's actually what we have here. So let's subtract the x squared over. So y squared equals 4 minus x squared, and y equals the square root of 4 minus x squared. This looks suspicious. In fact, what this means is that this function is its own inverse. Kind of like, do you remember the function 1 over x, which actually showed up in your homework? 1 over x is its own inverse. So if you do 1 over x and you do it again, you get back to the identity function. Same thing happens here. And you can see that if we go to the graph. I think I mentioned this is a circle. This has to take you back to your geometry days for a second. Circles have the form x squared, well, circles centered at the origin, have the form x squared plus y squared equals r squared. So and r is the radius. So 4 is my radius squared, then my radius is 2. Now, this can't be my function. Why? That's not a function. It doesn't pass the vertical line test, right? So, but you notice this is the positive square root, so that means it's the upper part, okay? So this would normally be the function 4 minus x squared. It's kind of, that circle looks a little lumpy. But you'll also know that the domain is restricted, and you can see why the domain has to be restricted, because if we were to draw our little line y equals x and flip, we would end up with something that's not a function. So in order to get a function, what we're going to have to do is restrict the domain, and in this case we restrict it to x bigger than or equal to 0. So we're going to delete this part. So the function looks like just that quarter circle right there, and I'm going to adjust my line. It's going to be important that I adjust my line because I really need it right there at y equals x. Okay, so now you'll notice that if I flip this around, the line y equals x, the inverse function that I get is actually the same function. So that green one is the inverse and the original one is the f. So lo and behold, that is what happens with a quarter circle there. Does that make sense? Sorry, I'm standing in the way. Any questions? Well, I guess you can ask questions, but unfortunately I can't answer them. So hopefully this made sense. Let's go ahead and grab number 45 now. Okay, so we're going to try number 45 here. Word problems. Everybody loves word problems. Okay, so suppose you need 50 pounds of two commodities costing $1.25 and $1.60 per pound. Verify that the total cost is this, where X is the number of pounds of the less expensive commodity, okay? So here's what I want you to think about here. We've got two commodities. I love how they talk about commodities. Let's maybe talk about products. So I've got a product number 1 and a product number 2. I'm just making something here. And the first thing that I make costs, the cost here, well, let me, I have an amount that I'm going to make, and I have a cost that sort of a cost per unit that's going to cost. So the first product costs me $1.25 per pound, and the second product costs me $1.60 per pound. Now, the number of pounds that I'm going to have between these two things, what they tell you in the problem is that you need 50 pounds total. So whatever I put here, these two things together have to add to 50 pounds. So I don't know how much that is. That's actually part of the point of this. So what I'm going to do is I'm going to name the number of pounds of the first thing that I'm making X. So then the number of pounds of the second thing that I'm making would be, these things have to add to 50, so the second thing would be 50 minus X. Okay, so the first thing would be X, second thing would be 50 minus X. And so now, let's see, now I want the total cost. Well, the cost for the first product is the number of pounds times the cost per pound. So the total cost for making the first product would be 1.25x. See that? And the total cost for making the second thing would be the cost per pound times the number of pounds. And so now the total cost of making both all of this product here, product number 1 and product number 2, the total cost, which they're calling y, is going to be the sum of these two. So that is the total cost of production. Okay? Okay, so now, hopefully that's clear, that's part A. Let's simplify that because, well, in part B we're supposed to find the inverse function. So let's start with this function here, 1.25x plus 1.6 times 50 minus x. Okay? So now I want to find the inverse function. Now, to find the inverse function, I like dealing with functions that aren't too crazy. So I'm going to simplify this function a little bit first. I'm going to write this as 1.25x plus, and I'm going to multiply this 1.6 out. So I'm going to get 50, 1.6 times 50 is actually 80. And then minus 1.6x, so we multiply the 1.6 on both things. And then combining these two together, negative 1.6 plus 1.25 gives me 80 minus 0.35x. Okay, that's a simplified version of my equation. So to get the inverse function, what I'm going to do, I'm going to switch x and y. And then solve for y. Good. So let's solve for y. So I'm going to add the y over here and subtract the x over here, kind of like I did with that previous problem. So I'm going to get 0.35y, adding that over, equals 80 minus x. I'm going to subtract the x over. And then if I divide by 0.35, I get 80 minus x over 0.35. Okay? So that is my inverse function. Now I want you to think about this just for a second, what this means. This function over here, which was my original function, the x signified the number of pounds of the first product, and the y represented the total cost. In the inverse function, remember the inputs and outputs are now switched. So the x represents the total cost, and the y represents the number of pounds of the original thing that I'm producing. So I would use this equation if you're telling me, let's make 30 pounds. What would the total cost be? So if I give you that this is 30 pounds, what would the total cost be? The purpose of the inverse function is to ask the opposite question. If I wanted a total cost of 20 bucks or something, I don't know what could go in here, but if I wanted a total cost of 20 bucks, how many pounds would I need to make of this in order to have the total cost be $20? So I could plug in 20 and figure out what this thing is. So it's asking me if I'm asking the reverse question, the inverse function allows me to answer that. So if you think about the domain of the inverse function, what we're really asking is what type of total costs can I have here? And to maybe think about that, let's first think about what the domain is of the original function, okay? What if the total number of pounds of this stuff that I'm making is 50, what are the possible numbers that can go in here? I can't have negative pounds, so we can't plug in negative numbers. I could have 0 pounds, so my domain is 0, and it really does include 0 because I could make 0 of this product and 50 of this product. And it goes all the way up to, the biggest I could have here is I could make 50 of this and 0 of that. So the domain there is from 0 to 50. Now I want you to notice that this inverse function, the original function, which we simplified here, is just a line, right? So it's actually a line with a negative slope. Kind of looks like that. So if I want to figure out the domain is 0 to 50, the range would be what I would get if I plugged in 0. Okay, if I plug in 0, the cost would be 80 bucks. And if I plugged in 50, the cost, let's look at here. So I'm just going to take my calculator out. 0.35 times 50. Okay, and then I'm going to subtract that from 80. So I get $62.50 here. So the range of this original function here, which is this one, the domain is 0 to 50, and the range is 625 to 80. When I take the inverse, what happens to the domain and the range? The inputs and outputs. They switch, right? So if the range of this original function was 62.5 to 80, that means the domain of this new inverse function is also going to be 62.5 to 80. So the key here for this problem is that the domain and the range switch. Okay. And so now, because of the way the inverse function is set up in part D, if we want to determine the number of pounds that we would get if the total cost were 70, that's exactly how this inverse function is set up. I plug in 70 right here, and I can determine some number of pounds of this commodity, which is the less expensive commodity, which is the one that they're asking about. Okay. I hope that made sense. Do your best, and if we've got further questions, I can talk a little more about this on Monday. But the point is, inverse functions allow you to take, instead of going from inputs to outputs, we're going backwards from outputs to inputs. So instead of going from number of pounds to total cost, we're going from total cost to number of pounds, and it lets me do these calculations fairly easily. Okay. Hopefully, number 66, I think I'm going to skip number 66, but hopefully you were able to draw it and eliminate, if you're doing that absolute value of x minus 3, I would probably kill the negative, like the left side, which I guess for you would be this side. And then draw in your line and flip it. So it's going to look like that. Okay. So give that a try. You guys can talk to each other if you have some questions, but I think hopefully overall that makes sense. Okay. You guys good? Okay. So remember, so when we were talking again about inverse functions. And we talked about how to get them graphically and algebraically. And the concept behind it, so graphically, we take our function, we've drawn the line y equals x, and we flip everything. Hopefully it's a function. If it's not a function when we flip it, we've got to restrict that domain. We've got to cut it. So what we're talking about is a function. We're not really going to see that today in what we're going to talk about with logs. We will see that some tomorrow when we're talking about inverse trig functions. So algebraically, we saw that just in the homework here. You switch x and y and solve for y. But the concept is that f and f inverse undo, which I'll put in quotes, undo one another. And what that means is if I do f and then f inverse, remember we're talking about composition, if I do f and then f inverse, that's going to just give me the original thing back. That's just going to give me x. So they undo one another. If you want to think of them as canceling, that's fine. Or if I do it the other way, if I do f inverse and then do f, those cancel each other and I'm left with the original thing again. Okay? So what we're going to do is we're going to try this with a specific function. We'll do it with an exponential. Look at what the inverse looks like. That'll give us a log, and then we'll kind of make it a little more general than that, and we'll go through a few laws and talk about evaluating, okay? So we'll look at this, we'll look at this conceptually, graphically, algebraically. We'll talk about evaluating, okay? So let's do this with a specific function. I'm going to erase some of this. This will just give me my list of, so conceptually, graphically, algebraically, and evaluating. This is kind of what we're going to do with logarithms today, okay? So let's take the function 2 to the x. All right, and before I do anything, I want you to draw this function. We've done this a couple times. You should be able to just go whoosh, whoosh, and then I'm not going to give you the next motion. What does it look like? You have to have this in your brain. If you don't know this function, you will have to put it on an index card and memorize it because you need to know what this looks like, okay? Should take you 10 seconds. And then it can actually, you should probably be able to do it in like 2 seconds. And then I don't want to give it away. Okay, what does this look like I've been stalling for you? It looks like this here. Okay, it goes through 0, 1, and it goes up, if you remember, at 1. When you plug in 1, you get 2. When you plug in 2, you get 4, so it goes up pretty steeply. Okay, and it hugs the x-axis over on this side. So the first thing that we're going to do is we're going to ask, can we get an inverse function for this? And you remember, in order to evaluate that, what we have to figure out is this function one-to-one? In other words, if you kind of want to, there's a way to cheat and do this. If you try flipping it, you can try flipping it and see if you actually get a function. But if you remember, the way this works is if I flip it and don't get a function, the inverse is not passing the vertical line test, which means the reverse one is not passing the horizontal line test. So what we need to ask here, if we want to say, is there an inverse, is we want to say, does this pass the horizontal line test? And the answer should be yes, it does pass the horizontal line test. So we're going to flip it around that line, y equals x. Remember, this is our line, y equals x. And when we do that, we kind of tilt our head. And I should actually just give you guys a minute and let you try to draw in this inverse function. Okay, again, just kind of think symmetrically, if you tilt your head, one of these is going off this way, the other one should be going off this way. If this one's hugging the x-axis this way, the other one should be hugging the y-axis this way. Okay, so take a second and try to draw that. Okay, and what you should see, you should get a function that looks like that, so that green thing. And instead of going through the point 0, 1, this one goes through the point 1, 0. So this is the inverse function. And the inverse function for this exponential 2 to the x, we're going to give a special name. We're going to call this a logarithm. We're going to call this log base 2 of x. Okay, that's just a name. That's all that we're doing is we're naming this is the inverse function for 2 to the x. So the inverse function for 2 to the x is log base 2 of x. Okay? Make sense? So you'll notice that this function, whatever this is, we don't really feel very comfortable with logarithms yet, and we'll see what's going to happen with that. But it starts, first of all, one thing that I notice is that the domain of this function is 0 to infinity, but not including 0. So you're not allowed to plug 0 into this function. You're not allowed to plug any negative numbers into this function. And the reason is that, well, we'll actually see the reason in a second. So that'll make sense in a second. Another thing that I notice is that this function does go through, it goes through 1 comma 0. So that means when I plug in 1, I get 0. And there's a reason for that that we'll talk about in a second when we talk about evaluating functions. So we're just kind of looking at it right now. Okay, now I kind of stopped and I wanted to shift gears just for a second because I think I want you to truly understand why do we have these inverse functions? Why do we have this idea of undoing functions? Before we talk about using logs, because I think logs can be very confusing and we kind of go, what's the point? Most of the time, one of the key reasons why we have inverse functions is we want to solve equations, okay? So let me give you an example here, a real simple example so you can kind of see what I mean. If I've got 4x equals 8, you can kind of do this in your head. But I want you to think about what's going on here for a second. I'm taking my x and I'm applying a function to it. What function am I applying here? This function is f of x equals 4x. Now, what would you do to actually solve this equation? What would you do? You'd divide by 4. Why? The reason is that dividing by 4, that's actually the inverse function. That's the opposite of 4x. Remember, the inverse function for 4x would be 1/4 x, or x over 4. So what we're doing when we solve this equation effectively is we're taking this equation and then we're applying the inverse function to both sides. So we're taking 1/4 of this and 1/4 of this. And the nice thing about inverse functions is that they cancel each other. So what I end up with on the left side is x, and what I get on the right side is, in this case, I get 2. So I can solve for x. Okay? Does that make sense? Let's try it with another example that's fairly familiar, and then we'll do it in kind of a weird example. So what if I had the equation x squared equals 9? Okay? And I want to solve this. Now, notice that the function that's here is f of x equals x squared. Remember, that doesn't quite have an inverse function, but we're going to assume that we're just taking the positive part so that it does. We're kind of cutting it. The inverse function here, what would you do to solve this? You would take the square root of both sides. And what you're effectively doing is you're taking that inverse function and you're applying it to both sides. So when I have this equation, I'm going to apply the inverse function to the left side and apply the inverse function to the right side. And these two functions cancel each other because they're inverses. And what you get is x equals 3. Right? So in general, if I've got a function, f of x equals some stuff that maybe doesn't make me happy, the way that I try to solve this equation is I apply the inverse function to both sides. And the function and the inverse function cancel to give me x. Remember, that's a property of our inverse functions. If you have your function and you take the inverse function, that just gives you x. Same the other way around. If you have your inverse function, you apply your function, they cancel each other, and you just get x. Okay? So we're going to do this in the case where we're talking about exponentials, and you're trying to solve an equation involving exponentials. So let me show you what I mean here. Okay, let's suppose I give you the equation 2 to the x minus 3 equals 5. And I want to solve this equation. And again, I want you to think of it kind of like x squared equals 9, this equation. The first thing I do here is I look at what's over here and I say, how do I undo it? In this case, I take the square root because that's the inverse function. Over here, how do I undo 2 to the something? Well, the inverse function for that is log. So log base 2, what I'm going to do is I'm going to apply that function to both sides. On the left side, these two things cancel each other, just like the square root and the squared cancel each other. And I'm left with something super simple, x minus 3. On the right side, I get log base 2 of 5. Now that's a number. I don't know what that is. Think of it as like 2.4. Just making something up. So if this is x minus 3 equals 2.4, the way that you would now solve is you just add 3 to both sides. And that's your answer. Make sense? Let's try another example here. Let's suppose that I have log base 2 of x squared equals 4. Okay? So again, just like with my x squared here, I'm thinking what's the outermost thing, how do I undo that? So the way that I undo the log function, the log and the exponential function are inverses of each other. So the way that I undo that is to take 2 to that side. Same thing over here. So I take 2 to both sides. And that 2 and that log are going to cancel, and what I'm left with is just x squared. 2 to the 4th turns out to be 16. Okay? And then I just take my square root, again doing an inverse function, I take my square root and In this case, we're just going to take the positive square root, so my answer is 4. Technically, it could be plus or minus 4. Does that make sense? So the part of the real point and the real power of inverse functions is solving equations. The other thing that usually freaks people out about logs is evaluating logs. How do I actually put in a number? How do I evaluate a log? So let me give you an example of what I mean. Log base 2 of 8. That's actually something you can do in your head, but you have to understand what's going on here. Okay? So to understand that, let me erase some things here. I want to, again, back away from logs because logs can be really super confusing. And I want you to think about a context that's not too hard, but you can kind of understand. So let me go back to the idea of square root for a second. If I were to say, what's the square root of 16? The answer is 4. But I want you to think about why the answer is 4. The answer is 4 because what the square root of 16 means is, what this is asking is what squared is 16. What squared is 16? Okay, now notice this is the inverse function of the square root. So if I don't understand square roots really well, but I understand squaring really well. So this is a hard question for me to answer. This is a much easier question for me to answer. Okay? So let's try it with a different one. Cube root of 8. What is the cube root of 8? Well, cube roots confuse me. So what I'm going to do is I'm going to think of, well, what is this asking me? It's saying what cubed equals 8. Well, that I can kind of figure out in my brain. I think that turns out to be 2. Okay, so when we get a function that's hard for us to evaluate, if we can think about what the question looks like in the inverse case, then we can actually solve it. Okay, so let's think about this question for a second. Log base 2 of 8 means what? Well, what it means, if we were to think about it in the inverse sense, it means 2 to the what is 8. 2 to the what is 8. What's the answer to that? Well, the answer there is 3, right? So this turns out to be 3 here. So if we can translate a log question, which is hard, into an exponential question, it's much easier and I can solve it. Okay? So let's take another look at an example. Log base 2 of 1. What does that mean? Well, if I translate it into an exponential question, 2 to the what is 1. Do you remember 2 to what power is 1? 0. Okay, so the answer turns out to be 0 here. What about if I were to say log base 2 of 1/2? What this means, let's translate it because this is confusing to me. This means 2 to the what is 1/2. Do you remember what power we take 2 to get 1/2? We take it to the -1 power, okay? So if you run across questions in the homework eventually where you're supposed to evaluate logs, many times what's a whole lot easier to do is to turn the question around, just like you would with square root or cube root. Turn the question around and ask, what is this saying about an exponential? What is this question in terms of an exponential? Okay. Now, there's nothing special about base 2. If I were to do this with base, whatever, base 3, base 10, we generally refer to this as base a to the x. The function that we get when we take the inverse is log base a of x. Okay? And again, log base a of x, you'll notice it has domain it has domain 0 onward. You can't actually plug negative numbers in here. If you want to think about why that is, think about plugging a negative number into log base 2 for a second. Log base 2 of negative 1 means 2 to what power is negative 1? Well, you can't take 2 to any power and get a negative number, so this does not work. Right, and that's truly why these logarithms, that you can't plug in negative numbers or 0. You can't take 2 to a power and get 0 either. Okay? So these logarithms are set up so that log base a of x, when I do that function and then I take a to that, they cancel each other. And when I take log base a of the exponential, that also cancels each other and I get x. Okay? So that's how these functions are cooked up. Okay, and there's some laws that I'm just going to mention here. If you've seen logarithms before, you've seen these laws. I'm not going to prove how these laws work. But there's these laws like log base a of xy equals log base a of x plus log base a of y. Right? Do you remember these? So if you multiplication on the inside becomes addition on the outside. Division on the inside becomes subtraction on the outside. And then the third law that is generally used a lot in logarithms is that if you have a power on the inside, you can pull it out front. Okay? So if I have a log of x to the r, I can pull that power out front. Now I'm not giving any justification for these laws. I could prove to you why these are true, but I don't think that's going to be helpful here. But these are 3 laws about logarithms that will come up later. Okay, so you should be familiar with them. If you've never seen them before, you need to learn them. You can put this on one side of an index card and this on a different side. But learn that when you have, like if I have log base 2 of 3x, I can write that as log base 2 of 3 plus log base 2 of x. Okay, that's like, that would be applying this law here. Okay, so these are laws that you need to know. There's one very special one special log, and that is when the base is e. Do you remember this? E is that special number where this slope is 1. E is about 2.7. When the base is e, log base e of x, we usually don't write log base e of x, we write ln of x, and this is called the natural logarithm. And I indicated before that this number e has some very special properties, and this is kind of the natural number to use here. We're going to see why later on, when we get into calculus stuff, why we would want to deal with this number e. But the log base e of x, we give this a special name. It's the natural log. Sometimes you'll also see teachers write log base 10 of x. That shows up a lot in science. Sometimes you'll see books write this, log. This is terrible. Don't ever write this, please. Log, if you're in science and you write log, it means log base 10. If you're in math, many times it means log base e, natural log. So it gets really confusing. Don't write log. You can write log base 10, or you can write natural log, but don't just write log and leave off the base. Okay? So hopefully this dusts off some cobwebs for logarithms. I'm hoping this wasn't too confusing here for you. If it got pretty confusing, we'll go over some of this on Monday. We can talk a little bit more about it if you've got some questions. There's no homework for tomorrow, but there is a quiz. And the quiz is going to be over domains of functions, drawing piecewise functions, trig functions, kind of evaluating trig functions, kind of those questions that I've asked toward the beginning of class. Those are the types of things that you'll see that'll show up on the quiz tomorrow. So have a great day. Have a great service time this afternoon. Stay safe. Shine for Jesus. And I will be joining you again by video tomorrow. Take care, guys.